Hi everyone, this is a research track project and our presentation is about word embedding and other general graph embeddings. And our topic is race relationship aware social embedding. We have team members Ji Yang, Yun Hao, and Wenyi Lu. Before we begin, we'd better look back to see how embedding works. The idea of embedding itself is to convert everything into factor and represent them using a higher dimension space. So let's take an example of social network. Each user could be represented as a factor. This factor length could represent in how many friends you have or how many topics you are interested in. Dimension could be quite high. So for social networks, you have hundreds of friends, so you have hundreds of dimensions. This could bring both advantages and disadvantages. Advantage is that as dimension becomes higher, each dataset are more separated with each other. The cost accordingly is that the data would be sparse in high dimension space, but more ordered. We could see in the left map that each dataset will become smaller and more separated with each other. Namely, they have a higher or larger distance with each other datasets. This could be good. We could also see in the right map for 2D dimension, all data seems to cluster together. But in a 3D dimension space, we could get a clear curved dimensionality. Similarly, people could use embedding to compute a specific dimension space, and the data could be close to each other if computed in appropriate ways. Now let's take a look back at the Sybil and skipgram right now. As we know, it uses a factor to represent words, so the algorithm becomes typical word-to-factor or factor-word algorithm. And below is a map showing the workflow of Sybil. And skipgram is just the reverse workflow. Workflow input matrix has a size of phi multiplied by n, where phi is the size of dictionary. N is the size of setted hidden layer dimension. We often set it to be 128 dimensions, but it could vary according to your own interest. Word embedding output matrix has a size accordingly of n multiplied by b, and getting the results in fact becomes a problem of training these two matrices. Sybil realized its own function by copying c times of the word two factors. Namely, you get various of word input matrix, and you have to train all these matrix and parameters during your input procedure. C is the length of the short sentence that you adapt to, namely the sliding window. For the aspect of neural network, we could see clearly here that this workflow in fact is an algorithm with just one hidden layer training, namely not so deep, or not deep enough to contain too many latent factories. This is where we can have something in it and dig deep into it. Traditional machine learning technologies mostly use low-dimensional structure in a high-dimension space. These algorithms often accompany with affinity matrix, which has the size of n multiplied by n, namely n squared, and many inverting matrix procedures happen during your processing, which are too slow in most conditions. This is so bad, but it also has some advantages. It's pure mathematical algorithm, so the results are reliable and very accurate. These methods often include classification, clustering, and regression, and we just list some of them here. Isomap, Laplacian eigenmaps, egg maps, LLE, kinds of these things. They all leverage data manifold, which is accurate enough, but becomes so slow and not so efficient. Now we have deep learning approaches. Deep work leverages the problem of path sampling, converts a network into a sequence of paths, which are similar to sentences in text mining. So deep work could also be used to leverage some successful neural modes, like skipgram, we just said, could give a higher efficiency for word embedding, which is a breakthrough on efficiency. Similar work we have right now also listed, like line and node2factor. These projects will later serve as our own project's baselines. We here also introduce the Node2Factor project briefly. This is a project aiming at creating a framework to fetch scalable graph network features, namely a scalable feature learning framework. It uses random walk to serve as sliding window function, which just like skipgram does. So we could not only use it in word or corpus conditions, but also use it in general graph nodes conditions. Namely, the algorithm could also have nonlinear functions other than linear conditions. Input a character graph and output would be a set of representations. It is also a good baseline to see how good our own implementation is to do word embedding compared with general nodes approach to graph. Also, we would use this node2factor algorithm here for non-directed graph. Word embedding doesn't care about how they are connected, but in real life, different connections often have one or two reasons to explain why it is connected, namely the semantics. So here we'd better introduce social embedding to the computation of skipgram, where relationship matters in this graph. Different corpus have different dimensions, and for example, in a corpus that introduces many friends, you want to know how these friends are added. Some people have common friends, namely friend relationship, you have the same group, or the common topics, you have the same topic. These are both reasons in different corpuses. And this also means different dimensions have separated spaces. Some people could be quite close in friendship relation in the friend dimension space, while these people at the same time would have a relatively longer distance in neighborhood relationship. Traditional word embedding calculates this distance only according to random walk steps or graph distances. They just mix all the corpus together into a whole graph and use a random walk or SVM, these typical methods to calculate the distance. But social distances change with relationships. Social embedding is originally designed for word embedding. One distance close often results in far away in other dimensions, as we told above. Namely, we could use the best semantic dimension space serving as a clustering function. Namely, we could just focus on some major distance in some specific distance. The embedding itself, well, is homogeneous. So what we do, as we just focus on some major distance in some specific distance, we could just use projection as a filter to get the dimension space we really care about, as we see in this slide's left graph. Each project space is a relation space. The entity space could map itself into different relation space, marked as R1, R2, R3, and so on here. With each dimension space mapped, we could get this relation's distance in certain relation space and compare different distances over different relation spaces. Getting the closest one would also result in the word embedding result in the word corpuses. And this result comes with the explanation of how it is found, namely which relation space it is traced and located in, and which relationship space does this pair have the closest relationship. Namely, every connection could be explained. Based on the skip-gram network algorithm, the equation shown above, our approach is to introduce a relational matrix R and change the equation to the equation below. To explicitly model different relationships, the likelihood would be all possible connection evaluation concerning the relationship R. R means the weights are concerning with different dimensions. We could make the initial value to be just one topic's dimension all set to be 1, and all the other topics to be 0. After several iterations, the weights would be more distributed as we calculate the likelihood using integration. This R matrix in each relation space could also be represented as a set of factors, each factor with certain amounts of elements, serving as a single hidden layer element. This could be a metadata and set to any numbers like 100 or 28 or around. Our target is to customize authors to their most active venue, so they could get in which dimension space they could be mostly close to each other. We could also see from another aspect, namely the neural network viewpoint. Transferring skip-gram formula into ours means we embed a new layer between the input and output besides the skip-gram hidden layer. We have said in above slides that skip-gram workflow just has one hidden layer, and now we add one more. This hidden layer has clear meaning. We don't know whom to cluster into this topic, or semantic reason why should we connect with each other, but we know that each connection have the latent reason to belong to this layer, or everyone generate their links through this layer. Well, we could set each of the matrix first dimension as k. This would be just mean that we suppose there would be k latent topics. Also, each topic has m dimensions. We suppose they have m dimensions. This means that each topic has m factors to be affected. After training the R matrix, each weight got a number. Then we could tell which topic impacts this connection more, and the possibility factor, or the matrix itself, could explain what's the social connection semantic, and you could just select the one with the maximum number. And meanwhile, we could also know how to make the likelihood maximum at the same time. We optimize the likelihood using the traditional EM process and this step here. For the E step, we compute each PRD weight, and then use variance inference and integrate on a multivariate Gaussian distribution. Also, as we could take the advantage of constraints of R parameters, we know that the meaning of R weight means how many distribution or how much is it possible to be for this person to be influenced by this K topic. So the possibility of R would sum up to be 1. This is one of the constraints. There are also other constraints which we could take advantage to make a calculation much easier. For M step, we compute embeddings with gradient descent algorithm, which would make the likelihood maximum after several steps. For the evaluation, We here use the dataset of DBLP data, which has all the DBLP paper information before 2016, November the 2nd. The data contains information about all the authors of the papers and the titles of the papers and many other information. What we want is to find out how familiar are these authors to each other. Different papers have different conferences. So here, as the implementation of social embedding, we use conference information as different topics. If an author prefers to present his or her paper in this conference, this would be a relational data space, and the people close to each other in this space would probably result in them clustering and become embedding pairs with each other. And we could also know how much does this conference paper contribute to them to become embedding pairs, as we can get a hidden layer possibility. The size of the data after processing for these three conferences is KDD, ICML, and VLDB are 21,878 authors. For these three conferences, we have totally 101,000 links and 588 links. Namely, meaning co-author relationships means that this author has co-authored with another author. And we also trim the duplicate same connections before that. Namely, if one author co-authors with the other author many times, we just count this as one for the paper map to build. First, we just project each conference authors and their connections to each relation space. Then, try to find out under which relationship do these authors have a closest connection with the others. This is basically the process of changing the embedding factor also. If one is closest to the other one in a relation space, that means that he probably would choose this conference as the most possible reason to be an embedding pair with the other. So for the baseline, we will also compare the result with deep work and node two-factor result. Both of these datasets are without distinguished relationship datasets. For the evaluation, we here use three ways to do implementation and verification. The first one is clustering and visualization. Namely, we map all the result data into a 2D coordinate platform to see how the nodes are distributed. The second one is also two-value classification, namely how accurate is our method to be able to be classified to the correct value. Here, namely the correct conference for this author to attend. This method would compare also using SVM to verify if it is close connection overall. The third one is the author-to-author link prediction, namely what's the accuracy for this method to predict an author is the embedding pair with the other author. Let's take a look at the embedding cluster visualization result. This is the result as we see learned from KDD popular authors. We could see from the graph about who is the most popular among these authors. If one is more popular, then he or she would be more located in the center of the cluster. And for each author, their nearby authors are the authors who probably interact or collect with this author quite often. Namely, the authors around a specific author probably would become a possible embedding pair candidates with this author. This is the author-to-value classification result with deep work and node two-factor as the baseline. This evaluation evaluates the accuracy for the authors to be classified into their most active value, and as we do cross-functional evaluation, we have various of training portion, varying from 0.1 to 0.9. So here we could see how the accuracy varies while the training portion descending. From the result, we could see Rase has an obvious higher accuracy than deep work and node 2 factor, while node 2 factor and deep work in average has similar performance in this aspect. This is because we add the social embedding information into it during the classification. This is the author-to-author classification result with deep work and node 2 factor as baseline. This evaluation evaluates the accuracy for the connections between author to author are correctly evaluated. Namely, this is the pairwise matrix to evaluate if two linked authors are embedded closer than two authors that are not linked. To verify this, we sample 1 to 10 non-linked pairs among the two links and put them into different baselines to see what's the average expected rate for different methods to trim the non-linked pairs. We could see clearly that no two-factor performs much better compared with the last time, but Rase still performs the best, showing that the social connection information that we implement here could really serve our target. For the future work, we think that we could do more mathematical verification of more efficient inference. Namely, we think that the EM algorithm and the calculation of PRD, this parameter, could be reduced the time in the future. I think in the future there will be other ways to compute the PRD more efficiently and more accurately. And for experiments, there are more case studies other than this dataset. So we could also use this method to implement using the other datasets and do case studies and have more interesting results and more interesting targets in the future. And thanks for listening. This is all for our presentation. Thank you.